Hey everyone, since I can't be there to give this lecture in person, I'm going to record some of my thoughts and statements on some of these slides for you guys to look over. Feel free to contact me with any questions you have about particle size. Obviously this is not the ideal way for me to do this, but we will make the best of it, so let's see what we can do. So the measurement of particle size is common in many industries, as you can see on the screen, the details of which and why it's important sort of apply to each field. And I will go through some examples that I've personally worked on and give you some context as to why particle size can matter so much for so many things. It has a lot of effect on materials properties, as you guys as MSE should know. It can affect things like strength. It can affect the color. Many people come up with, problems that come to our lab based on something looking a different color than something else. Some of the time that is because the particle size has changed, as well as composition or other features. Clearly systems can be very complicated, but particle size is one part of solving material science problems. So I'm going to go through some examples of things I've really worked on. After getting my PhD from Rutgers, one of my first jobs was to work on toilets. Not very high-tech or exciting as you would think, but there is a lot of complexity and design related to it. And one of the projects I had to work on there was discussing the strength properties of a certain toilet that was wall-mounted. And what was discovered through the work was that the component size of the ingredients that go into the kaolin and the rest of the system, the clays, the ball clay, the feldspar, and most importantly the quartz, the size of the components and the particle size control really did affect the strength of the system. So for porcelain, and you could find papers on this, the final fired composition has a number of phases. There's a glassy phase, there's a mullite phase, and there's the quartz. The quartz size affects the thermal stress, it affects the strengthening, it affects the crack behavior, and has a large effect on the behavior of the toilet bowl in terms of strength. So you have to have the quartz as the right size to have, strong toilets that would be mounted on a wall like you have in a hospital or facilities like that. After working on the toilets, I then went on to some other jobs, including optical fibers, another application where particle size filtration performance for making the raw materials, that relates very well to particle size. Having the right filter to remove things really improves the strength of systems like optical fiber, where a single large particle will cause the fiber to break. While working at H&M, like Dr. Miller does, I've done a lot of the particle size work. I've done work for an additive company where they would be putting certain interesting materials into their polymers to provide certain properties that they wanted, and based on particle size they could determine how long they had to mill the product to get the color behavior and to get other behaviors they needed without causing the filters to clog and shut down their whole process. So particle size is important once again. One of the really important things about particle size that I want you guys to take out of this lecture is that there are a number of different methods to measure particle size, and there are a number of different ways with which to interpret the data and which to consider your analysis. And all of these choices do matter to get you the particle size in the way that you want the results to best apply to your process. So with each advantage and disadvantage, when you make a choice as to how to look at your particles and get the numbers and shape information that you want, you need to be making the correct choices as an engineer to best fit your process and best fit the techniques that you have and convert between the techniques. And we'll talk more about this, but I'm really going to focus on these sort of 4 areas of measurement here. I'll be very brief on the microscopy, sedimentation, and sieving. I'm going to talk a lot more about laser diffraction because that's what I do. But understanding the different techniques that people use and how they need you to be able to go between them is important. I'll have customers call me with sieve data and want me to convert it to diffraction data by taking diffraction measurements. And I can do that, but there are caveats. And understanding the techniques is how we find these caveats and learn best how to give the customers the answer that they're looking for. And that same would apply to your research when you work with a certain tool or try to work something versus a paper. You need to sort of understand how you get the data you get from each technique and how to walk between them with the right sort of interpretations. So what is the size of a particle? You can consider particle size in the most simplest way. Look at it as being a diameter. That could work for something that's nice and round and you don't have any shape to it, but that's really not very realistic. Where some things in life are oblong, needle-shaped, acicular, rods. There are particles we measure for interesting geological features that look like flowers, florets, all kinds of things. Diatoms, they look like little, cylinders with holes in it. So you can easily measure something if you consider, one thing like a diameter, but you're also looking at something sort of two-dimensional that really is three. So a lot of particle size works off the assumption that particles are spheres, when in reality most particles are not. We do this because of math, to simplify some of the techniques and to give us consistent measurements. But we do need to understand that the data, any way you look at it, you should back it with actual, microscopy if you believe your particles are not round. You can use the particle size data considering the spherical shape, but that'll allow you to compare, different processing and different milling behavior. But if you want to know if you've changed the shape, you're going to need to look at the particles. So this is just something to think about as you do it. There are also different ways of defining size. A lot of this has developed out of early fields of looking at microstructures in metallurgy. These are different ways of comparing the size of a grain, and to be consistent when doing it on a picture that's already been taken optically or in electron microscopy. So you can look this slide over. I don't have to read it to you. You can read it in your own time. These are just different mathematical definitions developed by somebody to help you compare particles, understand when your particles are not spherical, how to do math that applies by calling things equivalent, spherical diameter. Things like that end up being important for particle size work. So we go through. This slide here is actually something, these slides are from the manufacturer, and this is something that they put together in a different form, and I've modified it to help you guys. One of the things that happen all the time are people look at particle size in terms of number counts and particle size calculations in terms of volume basis. This is important because when you do microscopy, what you're doing when you look at particle size, if you measure them in a microscope, that is inherently based on number. It's based on the amount of things that you can conceivably count and come up with measurements on. But the way that a laser diffraction system works is on a volume basis, which has an advantage in that you're measuring a much greater amount of something equivalent versus something real. By that I mean the way that the laser diffraction works, it treats all the particles as this equivalent spherical diameter, whereas it's not considering in microscopy the real shape. So when you do a number count on the real size of something, that is a useful piece of information on a small number of particles typically. Then when you go to laser diffraction, you're getting what is really the equivalent size, and you're getting it on many more particles. So understanding that the number of something that you have and how much that number of something will fit into a volume versus having equal volume and how much number you'd have of that. That's what the whole purpose of that figure 9 through 12 up top are. So the math that we do on particle size will work on a number or volume basis. And what the key to that is that you're counting either a lot more or a lot less of something, and you're counting either equivalent or real. These are just some of the considerations to make in terms of that part of the techniques. You also have to consider when you particle size test if you are looking for the actual particle size, or are you concerned with, because of your process, the agglomerate size. I have this talk with customers pretty often. People call me and want me to test a particle size measurement exactly as they send it, and I will sometimes say to them, well, your particles are actually smaller than they look like. They're just agglomerated. And if I don't break apart the agglomerates, you're not really getting a particle size. But sometimes for processes where you use a material, you do care about agglomerate size. So you have to consider that when you start to do the processes that happen during particle size measurement where particles can be broken apart to be measured, that's usually a good thing. If you want agglomerates, then that might not be the representative measurement you're hoping for. The condition of the material, if you're using it wet, dry, is it made into a paste? Does it travel in the agglomerated state, and is it being used that way? All of this is something you have to think about when I take a particle size measurement, and how does that affect the information that the customer, or for your thesis work or project, how does that convert into the information that you're really asking for? I know other Steve has probably talked a bit about microscopy, maybe not so much from a particle size sense, but clearly if you can image something, you could measure the particle size of it. Your advantages are that can be as simple as having a light microscope. Depending on the size of what you might need an SEM. But typically, it's an easy way to measure the size and shape of a particle. That shape information can be very useful to you if you need to know if your particle is a rod, or is it a sphere, or is it elongated in a certain direction? Does it look like a clay? Is it flat? Is there a shape factor to it? These are things you can see in a microscope that you can't always interpret directly from other particle size measurements. However, the issue with the statistics of particle size measurement when you do it microscopically is that it is a slow process that would require you to measure lots of particles to come up with any sort of true distribution math. The difference between measuring 30 particles on a single slide and saying that that is the distribution of a rail car worth of material versus measuring many more particles to come up with a true distribution by other techniques, that's generally the biggest advantage-disadvantage you get from microscopy. Later on in time, some of the particle size companies and manufacturers developed much better systems for automated microscopy, which is a fairly popular way to do stuff today for pharmaceuticals or other things that you can look at an optical level. Again, you prepare it on a slide, and now using computer control and thresholding by doing computer controlled type of image processing with conjunction probably of dyeing things, stuff like that. There's a lot of processes that can be involved here, but you save a lot of time because now it will take a picture and do the measurement. It will move over on the slide. It'll do another. So this is similar to doing it the other way, but now you've automated things to help you do some of the work. A very popular and historical method of particle size measurement is sieving. Your cost of the equipment, the directness of this. Again, you can size things the way you want. You can bin them certain ways. Historically, mining, geology, all the fields like that, soil people, they still speak in sieve and sieve numbers. There's not necessarily an issue with doing it this way, especially for historical fields like that, but it is very manual and there's a lot of work to it. There are also issues of what's the smallest size that you can sieve down to. You can't get sieves made below a certain limit, so you can't really go down as far as you might want to go. You can't do too much material at a time without having a lot of shaking and a lot of effort because the screen will blind. The material does stick a bit. Eventually, over time, hard enough stuff will distort if you have too much pressure on it. Some of your other disadvantages of this, interestingly, when you think about what a sieve is, it's a mesh with holes of a certain size. If I was to say take a needle, that was even a foot long, or a javelin, if it was narrow enough, I could technically orient it so it would go through the sieve in the other dimension because it happens to be of a shape that will fit through that hole when aligned in one direction. Now, in a random bounce inside of a sieve stack, that's not likely, but it would happen for a certain limit of particles, so you do have that kind of stuff happening when you're trying to take a really accurate measurement. So these are some of the issues you have. Even converting this into the other particle size data can be a challenge, but most of the particle size systems today have sort of an automated math that it'll do. So I can convert my particle size data to sieve and sieve data into representative particle size data. Sieving is clearly done by mass, so it's related somewhat to volume if you know enough about your material. So that's how you can do that kind of conversion, because laser diffraction data is done by volume. Another method that is still used both in a very manual, this is something you might do in a rudimentary type materials lab, you do like a Stokes law sedimentation. There are people who in fields to sort different silt out of systems, they will actually allow gravity to sort things out by particle size on a prepared slurry. So you can sort of use this as a simple way to measure by how things settle particle size. And there are systems that combine this type of sedimentation with laser or X-ray to give you a measurement of a particle as it falls through. Not super common, but it does work and it is an option. You will encounter this from time to time. This is just the math of Stokes' law. You can see that particles, the settling is related to the density, your fluid, viscosity, and the size. So you can go through all this math. I'm not going to do it here. You guys probably have seen this before, but this sort of holds for when you're trying to figure out how things will settle through a solution with time. If you want to have, this is sort of what you would use when you want to have something like a centrifuge and want to know what percentage of big particles that I get out by centrifugation versus what's left in the finer part of the liquid. You can use Stokes' law to help you determine that. I'm going to be brief on this one. This is sort of the end point of the sedimentation we just spoke about. As you have your loading in your solution and you go to measure this to do your sort of X-ray measurement by X-ray sedimentation, which is the most common one that I'm familiar with. Depending on the loading of your solution, the temperature change, you need to know density stuff. There's a lot of information you need to get sedimentation to work. So where it is a simple set of equipment, you might need to do it, and it is traditionally done in fields such as mining. They did this for a period of time. This is used for the clays. The analysis takes a lot of time to do. It also is going to suffer from a lot of this stuff like temperature variation. You need to record a lot of information. This has been replaced largely by all these laser diffraction particle size systems. And on the very low end, some of the stuff like dynamic light scattering that I'm not going to talk a lot about. But sedimentation has been moved out by techniques that are just easier to do. But it still is an option that you may encounter from time to time. So this will be the bulk of the rest of the talk, and this is the technique that I use at H&M, technique I use a lot in graduate school. It's the equipment that you guys would have the easiest access to at this point probably to get up and running to take these measurements for your work. Light diffraction, it's quicker than most of these other techniques. It's versatile. It also applies over a very wide range. It doesn't have that low-end problem with sieving. Even if you do have real true nanomaterials involved, it'll get you down pretty far. If you had to go any further, you'd go to DLS, which is a step beyond this. You can do materials that are wet. You can do materials that are dry if your system will allow it. You can specialize some of the conveying and other systems to help with the agglomerating for dry materials. You can do pharmaceuticals in low amounts. It's a really great, versatile, simple technique, and it's what I'll spend the rest of this talk talking about. This slide really talks about a lot of the stuff that you guys have been talking about over on the X-ray and electron end of things. What happens when light interacts with a particle? Many of the features that you've discussed in those other parts of the class actually apply to this as well with light. So some of the light that interacts with a particle is diffracted, some is reflected, there's refraction, there's absorption, re-radiation. There's a whole bunch of concepts that you guys have discussed in different ways. By knowing how light interacts with a particle, we can determine the size of what the particle is. By having knowledge of some of the optical properties of the material, the refractive index, both the real and imaginary, and understanding how a machine is set up to act with the diffraction of light, we can determine the size of particles. This is just a diffraction pattern from a particle. You guys have seen other stuff like this semester. So early on in the work on different types of light diffraction, people were doing these double slit experiments where you could look at the constructive and destructive interference pattern from light going through a double slit. What you'll find is that you have areas where you have constructive interference, areas where there's destructive interference, This looks just like what you're considering for X-ray diffraction, so I don't need to spend a ton of time on that. What is interesting is when you go beyond this and you take the next level. This is Fraunhofer's work on diffraction. This was based off of that double slit experiment. Now you start coming up with the math that relates to the wavelength. If you look at that equation over there, it should look very familiar to you. Again, this type of diffraction is actually very, 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 very similar, almost exactly to what you're having happen with X-rays, but now you're just doing it with the wavelength of light. So for your double slits, this is the math that holds. Interestingly enough, if you now create a pinhole instead of a double slit, it was observed that the same math applies. The situation is the same. Realization was that if you now put a particle and look at the scattering from the edges, that's the same exact behavior as you had before. So the point being, if you have light impinging on a particle, the diffraction at the edges of the particle tell you what the size is ultimately by relating this to the math. So this slide right here is the summary of that. No matter how you set up the experiment, if you consider it a slit, if you consider it just pinhole, if you consider it a particle, all of that math related to scattering are the same. Your diffraction pattern is the same from the edges of an object. So ultimately, this is your thought process on particle size by light scattering. Particles scatter light at angles dependent on their size. Large particles scatter intensely at narrow angles. The small particles are weak scatterers at wide angles. So by having sensors set up around particles and looking at how the light scatters, we can then do some math and optical modeling, and by taking the wavelength, we can come back to the size, pretending like it's a slit, like we saw before, and we will know the size of the particle based on how the light is scattering from them. The LA950 is the Horiba-made particle size light scattering instrument that we have at H&M. This is a very nice diagram of the setup of the system in terms of the light and how it works to measure the scattering. So you have a flow cell, which is that object in the middle. That's what your sample passes through. This can be in the wet system by being dispersed in a liquid. It can go through the cell. The dry powder drops through a similar cell. Then you have a laser. You shine it through that, and where the light diffracts to sensors that are arrayed around that cell will allow it to measure the size. There's a direct bit through that they use for determining the alignment and measuring the intensity of the laser. It does some system checks that way. What's interesting about this system, what they realized, adding a second light source with a different wavelength actually allows them to get better scattering information and more measurement over a different range. So they've added a second. Instead of just that red semiconductor wavelength, they have a blue LED light that they also use in a different position. So you can really get nice measurements out of this system by using this dual setup. So back to the concept of diffraction from large and small particles. For a large particle, you get low angle scatter, large signal, get high intensity. Small particle, you get wide, you get high angle scatter, small signal, lower intensity. So these are just looking at your pattern that you would get from shining it onto a single large or single small particle. You would get your ring like this. The sensors are arrayed so that it knows when it's looking at this pattern the size of the particle. I just talked about this a minute ago, but the two light sources allows them to change some of their scattering math and improve the results for finer particles. This is related to the wavelength and the optical properties of the sample. I'm not going to go through it at any high level, but by going to that blue wavelength, that second source, they were able to do different math of different scattering. You go from a Fraunhofer regime down to the Mie scattering regime, and now your particle size for things less than 20 microns, especially much less than that, your single digit micron and lower, the measurement is much better by using this type of system. I was just discussing how that they've improved the instrument to apply to different regimes by using the different light sources. The cool thing about the LA950 is that based on the information that you give it and everything else like that, it actually knows how to sort of best measure with what you have. So in terms of how it operates itself, you don't need to worry so much about that. The best thing for you guys to understand, and the biggest source of difficulty in particle size measurement, is in the actual sample preparation and choices you make to get a good sample for measuring particle size. The instrument is accurate, the instrument is reliable, it's usually very good at measuring things consistently. You can check standards, the behavior is very good. But you need to make sure that you have a stable dispersion of particles to get accurate measurement. In dispersion, I mean both dry and wet. Dry dispersion, you can do it in air, but obviously you need to make sure you have enough pressure to break things apart. Wet dispersion, you need to have the right vehicle for dispersing your dispersant medium. You might have to add things like surfactants to help it. You really need to get the particles well dispersed. You can't have things that are partially floating, reacting. So you really need to double check what you're doing beforehand and discover some of this. You also want to run multiple measurements, making sure that it's stable, making sure that you have enough ultrasonic to keep things broken apart. Look out for bubbles. The system will see a bubble like a spherical particle. So if you generate foaming, things like that, these are just practical things. Particle size is a very practical measurement. You need to far better understand how you're doing it than to really understand all the details of the machine. It's the sample making part that you spend more time on in getting good measurement. The optical properties of the material do matter for measuring things that are small. By small, I mean, less than 20 micron, it matters a bit. When you get down to less than 10, it starts to matter a lot more. Depending upon the shape of the particle as well, things that are spherical, things that are transparent, it matters to have the refractive index values better. When your particles are large, or your particles are, darker, particles are, especially not small, then your refractive index values don't matter. Because you do have to put work in to understand your index values when you really need highly accurate measurements of small things. And sometimes that takes effort in knowing your system. There are methods of taking measurements of refractive index. I don't do a lot of those anymore. It's just not something that we try to do. We get the information from the customer when I'm doing these measurements. But if you needed to discover the refractive index, you might have to do that work beforehand if you really want to get accurate measurements out for things that fit those conditions listed on the screen. So this just summarizes that this is when it matters most, this is when it matters least. These are things to think about when you're taking a measurement. This slide is somewhat the most important slide in this part of the talk. This goes back to what I said. The real key to doing a particle size measurement is understanding that the instrument error is small, pretty constant. The instrument does a good job. The key for making errors are in terms of the two things that you, and/or in my case, a customer, can control part of, and then I, as the person doing the test, control the rest of. Your errors in particle size measurement, by that I mean getting a measurement that truly represents your system, occur for how do you sample something, and then how do you prepare the sample. In terms of sampling, which here is labeled as extraction, how do you get a representative, proper sample out from your population of material? If you're testing for a rail car that you're buying of a raw product for your system, during the traveling on the train, something like a rail car of material, that's enough vibration where you'll shake all the larger things down. You will settle like sugar and salt when you shake them apart. The same thing can happen in your particle size samples. So you need to make sure that when you take a sample, you take it from a reasonably well-dispersed location. You need to shake the jar, shake the bag. You need to make sure that things that are shipped to you haven't settled. You need to make sure that you take a few measurements so that you're representing the population well. So those type of sample extraction errors can really matter, especially for large things because of that settling behavior we've talked about and in segregating populations. Then the other portion, which probably is even more important, is that sample preparation error. Did you properly break apart and disperse your agglomerates to measure your true particle size? Did you have enough ultrasonic? Did you have consistent behavior? Was the system showing instability so that you were getting agglomerates and then coming back? Are you not mixing it well enough so that your big particles are settling out? You control all of that, and your measurement error is related to how you do these two different things. For particle size distributions, there's really two types of distributions. Obviously, you can have combinations of many things, so they don't look this simple. But in a simplified basis, when you have a population of things that is really, really carefully milled or really highly, prepared, something like pharmaceuticals or polymer dispersions, which are used for measuring standards for particle size, they tend to be monodisperse. All your particles are the same size or roughly the same size. So what you have is a really nice, that's showing it as a rectangle, but in reality it's just a very nice, large, sharp peak because everything is roughly the same size. And then your math holds for that. And then for everything else in the world, just about, you have a much wider particle size distribution. You can have multiple modes, you can have a single mode, you can have a mode in one spot and then a mode further down and then a mode further down, depending on how mixed your material is. You can exist in many different ways, but clearly the math that you do and how you give the resultant data, if you have multiple modes and you just give an average, is that really representative of what you have? It's probably not the best thing to only give. So I always consider this when I'm doing particle size analysis for a customer. Do they need me to break down each of the modes? Do they need me to give them a span? What are they trying to do with the results? Again, stuff to think about. This is your particle size histogram or distribution. This is the output from a laser diffraction particle size measurement. It basically breaks everything down into little bins or channels. That's how it works, the different sensors, and it brings it up like this. It relates it by size versus volume. That's the standard way of doing it. You can change some of the channels. You can set things up a little differently. This is just what your output will look like. You can have a cumulative distribution that relates very nicely to sieve data because sieve data is given cumulatively. You can bring it up on screen different ways. This is just to give you a sense of output. The math is actually far more of what a customer asked me for than looking at the picture. So this is what I mean by the math, the parameters of describing a distribution. This is all stuff that you would have gotten out of your stats class, but it's sort of broken down into some industry-specific type terms. They're not even on this screen, but there's names for points in the distribution that people care about. I generally do give customers the mean, median, and mode, describing the peak, the 50% above and below, and then your weighted average, the center of gravity. That's what your mean would be. Sometimes, depending on your distribution, obviously, these points can be very similar, some of them, or close together. When you are, much more close to monodisperse, when you get to distributions with lots of different behavior, you'll get more deviation from that. But these are your basic stats. Much more often, this is sort of what your output data from a particle size analysis will look like, and these are values that people will give you. We just talked about the median, that's the 50 points, so half are smaller and half are larger. That's a good thing to have in your measurement. The D10, 10% 10% of the particles lie below that diameter, and then you have the D90, which is 90%. Typically, those three descriptions right there, the D10, D50, D90, describe your distribution well enough for you to have a good sense of your particle size distribution, especially when you combine it with your mean, median, and mode data. So that's a standard output that I give to a customer. One of the really key and interesting things on this, which I haven't read, and I do have this issue from time to time with customers, why would you not report a D100? That would mean that all your particles are below this size. That would be saying your largest particle is this and everything is below it. And you can understand why people might care about that in terms of filters or in terms of not wanting something above a certain size in your system. But that's a very statistically dangerous thing to do. If you believe any measurement can tell you that everything is less than this, then you'd have to really have faith or take enough measurements to sort of feel safe using that value. And you really wouldn't want to do that. You'd be better off taking multiple measurements and using a D90 data or D95, which you can sort of statistically go through. At D100 or D99, a single bubble of a certain size would be enough for the system to say that's your large particle. So that's just something to think about. Don't give statistics that you don't have good confidence in. And for particle size, because there's so much that can happen with the bubbles, with a hard single particle, the distribution of a certain agglomerate that you can't break apart in there, something that had been a little sintered, anything, especially on the large end, that will show up in your D100. And is it real? It may be, but you also cannot give the faith. So there's very few customers. There's one in particular who we use the D99, but they have a very special disclaimer on it that you don't want to talk about that. The D32 and the D43, those are also numbers that people will talk about. They actually have names. I don't remember them at the moment. They're not important. You can look them up. But they're just points in the distribution that people like to talk about when understanding the statistics. These all relate to typical math things, confidence intervals and everything like that. But this is a standard look for how to consider a particle size data. D10, D50, D90, very standard stuff. Physically, when you look at your distribution can be skewed. You can have positive skew, negative skew. This is pretty simple. You would want to consider this when you're looking at particle size data. This will tell you sometimes that something was bigger and it's been milled, because you start to get tails, and then the effectiveness of milling something down might not be as much. So typically when you have something that started out a certain way, you'd have that skew of finer particles as you start breaking it down, but then they don't break down unless you change your milling behavior. So this can tell you things about the material. It can tell you if something's been filtered to a filter size. Just something to look at and consider in your data. These are what real particle size data. These are all actually taken on my Horiba system at H&M. And you can see this is sort of the kind of stuff you'll look at. In that first one at top, you actually have what is a fairly narrow, very tall peak of a certain size, and then you have a lot of nanoparticles on the other end. So the math of that can be difficult. Your population is fairly monodispersed in one aspect, but you also have another mode of small particles. That second graph shows you there's really at least 3 modes in that data. You have 10 micron sized particles. You have something that's sort of over 180, around that range, and then you have something between 100 and 10 there with that shoulder. So that I would have to deconvolute to give accurate data. And then you have a nice, left skewed, standard looking distribution. A lot more things look like the second and third view than do the first, but this is just to show you what some real data looks like. This is to represent the reproducibility of something that you could measure in particle size, prepared with different ultrasonic bursts. So this is every 15-second interval of an ultrasonic pulse inside the wet system for measuring. This is methylcellulose. As you can see, for something that's in there and well dispersed and stable, your measurements don't change a lot. This tells you that the machine is very reproducible and very good at making a measurement. This also tells you that that specific product, as it was dispersed the way it was done, seems stable with ultrasonic. Some things with an extra ultrasonic will break apart more. Other things actually can agglomerate from ultrasonic. So this is sort of where I would take multiple measurements and judge the behavior of something to determine if I'm doing a good job as a particle size measurement person. This is a different look at a methylcellulose product prepared in a different way. Now you see that the ultrasonic and the application of it is showing that this is not a stable dispersion. You're getting different measurements based on the duration and the application of the ultrasonic. You also can change the setting of ultrasonic. This tells me if I was to give this to a customer, I wouldn't feel very good, because what is the real size of this? Obviously, it's starting out large, and then the ultrasonic breaks it down. But you need to have enough breakdown to be confident that it's done. How do you know at that 60 seconds it's finished? Because every time increment that you're showing here, it was still getting finer. I would have moved this to a higher level ultrasound and a long duration, or I might have to change the surfactant to make sure that I'm getting it broken down, because this is what it would mean when I'm not getting stability out of my system. This is just another output of that study showing the effect of the ultrasound on time, looking at the plateau of it, your D90, D50, D10. It tells you clearly the D90 is breaking down, more. Your bigger stuff breaks down from the ultrasonic more than your finer stuff does. The finer stuff you can't break apart any further with that level of ultrasound. This is just a nice little output from that methylcellulose study. That was actually not done by me, but it's very good data to look at. ISO 13320 is a method and procedure for doing particle size measurement, same as USP 429, that's used by pharmaceutical companies, and you have requirements for what is the coefficient of variation between the different measurements you take. So you take multiple measurements and you make sure that your standard deviation and then your COV, which is the standard deviation divided by the mean, you make sure that those are not deviating by larger than those amounts to be within the reproducibility limits. So depending on your application for pharmaceuticals, I might need to take extra measurements and do all this extra math just to show that the study is done properly. This last set of slides here is important to think about when you start converting particle size information between different methods. And in terms of if you had a project on milling, you can report particle size data in terms of number mean. This is done by counting particles. So if you have 10 particles of size 1 unit and one of size 100 units, the number mean, you can do it right there. You can see it on the screen. Your mean is 10. Now if I mill this, my largest particle breaks into 2. Obviously in milling you'd do it for a way that would break down, much more than that, but this is actually a thought exercise. So if I break that one particle, if I hit it with a hammer and it breaks into 2, your volume and mass are conserved, and now what happens to your number mean? So you've broken something down, so you've actually created one new particle, but how much does your mean change? If you look, according to this, your mean goes up to 14. So by breaking one particle, your mean has actually increased. If on a volume basis we now take 10 particles of size 1, 1 of 100, this is the same as we just did with number, and now we break the largest particle down into 2, and now we look at the D4, 3, that is a volume mean, that has a specific name in particle size, but we're going to call that the volume moment mean. That is actually one of the names you can use for it. Now, when you calculate that out after the breakdown, you've went down. This is actually what you would expect from the breakage of a particle when you look at it in terms of volume and not number. Because you broke a large particle versus having a lot more of a small particle. On a number basis, that dominates the behavior. So mathematically what you see isn't really what you'd expect for the breakdown of a large particle. So now, if you take the opposite effect, instead of breaking something down, we're going to agglomerate particles together. So we have 10 particles of size 1, and we have 10 of size 46.42. This is obviously done just for the math purpose, for this to work out, because this is a thought exercise. You do it on a number basis once again. There's your number mean. Now we agglomerate those 10 larger particles into 1 of 100. This is done for math. Obviously that ends up coming out to your 100 in volume. So now you've agglomerated half of the number of particles. So what happens to your mean? From a number basis, you've lost to 50% of your mean value in terms of number. This wouldn't make sense because you've agglomerated in that way. So now we're going to look at the volume mean. again, same number of stuff, and we're going to do the same thing. We're going to agglomerate that into one large particle. We've agglomerated half. Does the mean increase? Yes. Now when you do the volume basis, this shows what you'd expect. So the whole point of this thought exercise is to have you understand that two things about particle size that are really important are how you convert one method of counting to another, and how you do your statistics and how your understanding of it is. If you're doing things like breaking stuff down and you're trying to do this by microscopy, that's a number count. And unless you count enough particles, or you do it properly, obviously this is really simplified, but if you expanded this out, your understanding of your particle size behavior and distribution, depending on how you do the statistics and the math, can be very skewed and not really proper for what you're doing. Laser diffraction in a volume basis, because you're measuring more particles, or you're doing it in terms of a volume basis, you can actually keep your math much more in tune with what you'd expect. So you really need to just make sure that you understand this concept, that how you do particle size measurement, how you prepare your sample, how you compare it to other techniques, and how you do your math, how you report your statistics, all of this stuff is really important in giving you the information that you need to make the decisions you make as a material science engineer. Treating particle size like it is just a number, or it is just a value that the machine outputs without thinking about all this other stuff we've talked about, is how people run into problems in understanding the behavior of their system, clogging a filter, buying the wrong filter, too many filters. That's just an example. Over-milling your material with time, under-milling your material, misunderstanding the breakdown that's happening during milling. Particle size measurement can allow you to understand all of these processes that occur and better control your systems and your behavior. And this has a big impact on material science, so it's something very important to understand. I think that's the end of this. So I hope you guys learned something. Feel free to ask me any questions or send anything along. You guys should know how to get a hold of me. If not, Dr. Miller will refer you on, so it shouldn't be a problem. Have a good day.